Hello, everyone. My name is Cristina Garcia Miro from the National Astronomical Observatory and JUMPING Observatory from Spain. And I'm going to present this contribution with the name VLBI with the next generation of instruments that I prepared with the help of Sol Paragi, Richard Dobson, Maria Rioja, and many more. The content of the talk, I'm going to present global VLBI activities today, the VLBI capability for SKA and ngVLA, challenges and opportunities that this will pose for VLBI, and next decade science with VLBI. This is the global VLBI centimeter and millimeter landscape when we will include the next generation of instruments, the telescope SKA1-MID, LOW, and ngVLA. Nowadays, this global VLBI science is reserved to the projects that needs the highest angular resolutions. So sensitivity and UV coverage alone is not enough to qualify. This is for projects that requires the highest angular resolutions achieved from ground-based astronomy. To foster a truly global collaboration for VLBI and building on the 50+ years of experience, the established VLBI networks have formed the Global VLBI Alliance. And you can join the work group from the Commission B4 of the IAU to help with that project. So JUMPING JIVE project, Work Package 10, funded by the European Commission Horizon 2020 project, had the aim to provide the support for the SKA integration and operation within the VLBI networks. This work package was led by Sol Paragi at JIVE and Antonio Crisostomo at SKA-0, and I was the project scientist. We presented 4 deliverables in the project. The first one was the details of VLBI interfaces with the SKA consortia and requirements review. This was a quite easy task thanks to the wonderful and standing design for the correlator that was presented by NRC for SKA-MID and CSIRO and Astro for SKA-LOW. We also presented an operational model for inclusion of SKA-1 in global VLBI observations, with the definition of an SKA VLBI consortium, and I prepared that with the help of Sari Brim from SKA-0, and with the help of the science working group, the SKA VLBI science working group, and other international scientists. We prepare a portfolio of SKA science cases that showed that we needed more VLBI beams to cover all the science that we wanted to do. So we presented an engineering change proposal that was approved for alignment of the requirements to the design. And lastly, we have organized a workshop to discuss SKA key science projects that could benefit from the VLBI capability. So the VLBI capability for SKA1 is going to provide from 4 till 16 tidal array beams per subarray, and also primary beams from individual elements, antennas or stations to cover short UV spacings. Beamforming would be coherent for bore and off-bore side, for up to the whole array for mid, and the inner 20 kilometers for low. All these VLBI beams, pencil and primary, will have a bandwidth trade-off. Will provide in voltage VD format and will be correlated at an external VLBI correlator in the data transfer in real time or buffer. For multiband observations, we will use subarrays or frequency agility. And SKA will also provide imaging products simultaneously for VLBI calibration. And limited by resources, you will be able to get also other imaging products and non-imaging modes. Here you can see that depending on the size of the subarrays, you get certain field of views and sensitivities. So in a baseline with a 100-meter class telescope, a 1-minute integration, for mid, we can reach tens of microjanskis, for low, hundreds of microjanskis. The VLBI capability for ngVLA is quite similar. A single element, a single antenna will be able to participate in VLBI observations or the phase array output. The long part of the ngVLA will also work as a standalone VLBI array or integrated within the main array. The long stations, in principle 3 or 4 antennas, will be able to work like pair antennas for high precision astrometry, pointing to different locations in the sky or tuning at different frequencies. Multi-frequency observations will also be performed with subarrays or rapid switching between bands. This capability would provide from 3 up to 10 beams for VLBI with bandwidth trade-off as well and embedded format. And in this case, the ngVLA array will perform real-time correlation, including remote antennas such as the GBT, phase ALMA, EHT antennas, and possibly the electronic EBN, electronic LBA. So all these new capabilities that the next generation of instruments are providing to VLBI are going to realize what I've called next generation VLBI. So in short are the multi-tidal array beams that will be able to, that will allow us to serve large and multiple field of views for VLBI surveys and high precision astrometry, a boost in sensitivity, as these will be very sensitive elements that we will include in the networks, and also will push the expansion to lower in the case of SKA low, and higher frequencies in the case of ngVLA. These instruments will provide very good quality enhanced calibration products and exquisite RFI control. Both will cover global skies, complete surveys, so it will help to improve the UV coverage and VLBI networks expansion. And also the VLBI community is very enthusiastic about these prospects. So all these next generation VLBI will be able to cover unique emerging science goals. These new capabilities will pose challenges and opportunities for the next generation VLBI in 3 areas: technology, methods, and coverage and collecting area. With respect to technology and frequency coverage, these are the bands that will be covered by SKA1 and ngVLA. So global VLBI science will continue having its niche in L-band, C-band, X-band, K-band, and higher frequencies with ngVLA. So the individual elements of the VLBI networks are preparing as well to be compatible with these bands, developing broadband receivers like Brand EBN and the NASA's Deep Space Network receiver for global astrometry for VLBA. And this is the picture that we have in our JEDES, our 40-meter radio telescope, that we are also developing new broadband receivers to cover all your bands. And also we have the capability of simultaneous reception for K-band, Q-band, and W-band to do a frequency phase transfer. So all this will improve the sensitivity of the networks and will give us multi-frequency capability. With respect to wide field of view, the individual largest elements are installed in phased array feeds to provide multiple independent and stable tidal array beams. And at the higher frequencies, multi-beam receivers. So for our 100-meter antenna, we would need about 25 beams for VLBI to match the field of view of a 20-meter antenna. And these beams will be coincident for the next generation VLBI observations. And in correlation, we will need to consider multiple phase centers to access the entire primary beams. Other challenges and opportunities are with respect to coverage. Radcliffe has just started a SKA VLBI simulation task force last year and has presented EBN and SKA simulations that show a non-very Gaussian dirty beam. So the maximum sensitivity images are dominated by the spatial scales that contain the long sensitive SKA baselines. So this has an effect on the flux densities that are systematically offset due to this non-Gaussian dirty beam following the Jorsa-Tervan-Morsel effect. So in this case in particular, we will need to cover the gap in Africa. We will need to develop the African VLBI network. So that would be a very nice employed for the Jansky VLA antennas when they are decommissioned. With respect to methods, Rioja and Dobson recently presented a review of the next generation astrometric calibration techniques, and one of them is multi-view that can be applied to low and high frequencies to serve the target and many calibrations around target, and reduces the systematic below the thermal noise limit. Can use minimum 3 calibrators, but the ideal is 7 plus the target. So needs very many sensitive tidal ray beams with wide field of views, and can be used in beam mode, switch, or with pair of antennas. So with the next generation of instruments that have dynamic ranges over 1,000, this will provide a centimeter wavelengths, ultra precise astrometry up to 1 microarc, and will enable precise astrometry for much lower frequencies. For the higher frequencies, regarding ngVLA, the source frequency phase references will also have its niche. So next decade, for next generation VLBI science, in this SKA VLBI workshop in 2019, we studied the key science projects that could benefit of VLBI capability. And last year, CSIRO organized the VLBI in the SKA Era Symposium with more than 400 participants that saw the wealth of SKA VLBI science. And now I will present some examples of this next generation VLBI science for the next decade. For our galaxy, with multi-view technique, we will be able to expand the current census of major sources in the galaxy to be able to have a 6D tomography of the galaxy and beyond, surpassing the Gaia observable zone, and with the pulsars as well. We will be able to observe all the pulsars within our galaxy and up to the Magellanic Clouds. With respect to the transient universe, till date, only one binary neutron star merger has been detected in the electromagnetic regime. With next generation VLBI, we will be able to detect fainter mergers and help to cosmology to solve the sigma tension. With 10 mergers, the Hubble constant will be able to be determined with up to 5% error, 200 mergers with up to 1%. So next generation VLBI will be able to solve the viewing angle degeneracy for these fainter mergers. For fast radio bursts, we would like to understand their nature by host and galaxy determination and properties determination. So with the next generation VLBI, we'll be able to detect and pinpoint the fainter repeater population. Pulsar astrometry with ultra high precisions up to 1 microarc will help us proving the gravitational wave background, perform a strong field test of gravity, and study the ISM via pulsar scintillometry at low and high frequencies. For cradle of life, super flares on low mass stars can impact the habitability and biosignatures in the exoplanets. So next generation VLBI will help solve the degeneracy in these flare sizes and the strength of the magnetic fields. Precise astrometry will help to detect exoplanets that have microarc signatures, astrometric signatures in the stellar and substellar objects, and these signatures reveal the presence of low mass stars, brown dwarfs, and exoplanets. So with next generation VLBI, we'll be able to detect Jupiter-like planets around stars of 1 solar mass at 50 parsec with 100 microsecond signature, or planets like Earth at 15 parsecs with 1 microsecond signatures. And star-planet interactions produce coherent radio emission in M dwarfs that have terrestrial planets and Earth-sized planets in enclosing orbits or in the habitability zone. So with the next generation VLBI, we'll be able to measure the orbits of these exoplanets and prove magnetospheres and magnetic field strength in the system. For galaxies and AGNs, following the sample of the LOFAR 2-meter sky survey. At the lower frequencies, we will be able to probe AGN science. And for AGN and star formation disentanglement, characterization of Amaro Rayleigh galaxies, and radio loud and radio quiet studies of AGNs, and build a sample of highly resolved high redshift AGN. For the centimeter frequencies, we will be able to study how is the VLBI sky at microjansky sensitivities. So the VLBI beams will target the SKA and ngVLA deep field surveys to start all the radio and AGN science. Like these examples, like the observation of strong gravitational lenses. ngVLBI will increase the number of targets by 1,000 and will help in cosmology models. And also will help in the study to increase the coverage and sensitivity for study of mass accretion, jet formation, relativistic jet formation, and study of magnetic fields near supermassive black holes, like the example of M87. And here, to finish my talk, I couldn't stop commenting about this very nice result by Lu et al. Just made with the global millimeter VLBI array, in which JEVE's 40-meter radio telescope had participated, and they showed both the light brightened relativistic jet connected with the accretion flow. Thank you very much for your attention, and I will be very happy to take questions.
Hello, can you hear me? Hi there, Cristina. Questions for Cristina? There's one.
Thank you for your nice talk. From what I understand, MeerKAT will, MeerKAT will be included in the SKA, so there will be a transition for it. And yeah, so is there any path, or do you have any information about the inclusion of MeerKAT in the VLBI before being included in SKA?
That would be wonderful, because it will help us to prepare for the future. And I was attending the call that MeerKAT presented for the next year, for the observations next year. And I was very pleased to learn that they still have a VLBI capability in their plans. Okay, it may come later than maybe we would like, but they haven't thrown the towel yet. So yeah.
Later when?
I don't know, because I'm not MeerKAT.
Okay, thank you.
For me, the sooner the better, but I cannot tell you. What I could say, and I've noticed, is that they are so busy putting together the new modes, and so I don't know. You will need to ask them.
Okay, there's a question from online. And the question is, do we understand yet what the requirements are for the ngVLBI correlator? What how the computing model will work for VLBI with the SKA and ngVLA?
I don't think we know yet. So that's why we've established this simulation task force to learn about it. And the projects that are using multiple phase centers nowadays with the EVN correlator are crazy. You know, they could have a normal VLBI project just has one phase center, and these projects are using like almost 1,000 phase centers. Okay, so yeah, it's going to really change how we correlate the VLBI in the future, and it's something to take into account.
Great, let's thank Cristina again.